Now moving beyond the clinical diagnostics lab-on-a-chip applications, the next application that I want to focus on is something called deep brain stimulation. There are many neural disorders like Parkinson's disease and epilepsy and others. To address these neural disorders, deep brain stimulation is an approved, FDA-approved technique. In this technique, the surgeon drills a hole in the brain and implant an electrode, to stimulate the particular area of the brain, which is thought to be responsible for disorders such as epilepsy and Parkinson's disease. So typically these electrodes are carbon-based electrodes, and their size is about 1.3 millimeter in diameter, and they also have come with some contacts. So it is the stimulation of the brain is done in a crude way without any kind of feedback. When it is electrode which is larger than the necessary size, there are a couple of outcomes. One is generally the voltage that you put depends on the size. If you can reduce the size of the electrode, then you can reduce the voltage, and you can also reduce the pain that the patient suffers. That is one thing. And the second thing is these electrode voltages are applied 24/7, continuously, even though epileptic attack actually has got large intervals. It is not a continuous attack. And the same goes with Parkinson's disease. So there is no feedback here. And so possible improvements include making much smaller electrode. It could be a carbon electrode itself, but a much smaller electrode using the carbon nanofiber that I talked about in the case of the biosensor development. So this allows you to put the electrode in a precise location, so it could be a targeted activation. The other thing also is it allows you to reduce the voltage itself. Okay, then eventually you can do this in a closed loop system where you can get feedback information, essentially by measuring the concentrations of the neurotransmitters like dopamine and serotonin, and then you know what those ideal values should be if the patient were to behave normally, and then you compare actually the measured concentration to the ideal value, and when you see the deviation, then you can have a targeted activation of the brain in order to address the disorder. So this type of a closed loop system is possible with small nano electrodes. So here dopamine is one of the critical neurotransmitters which is thought to be responsible for disorders such as Parkinson's disease and epilepsy. I'm showing here the ability of the carbon nanofiber electrode that I talked about earlier on in the case of the biosensor development. The ability of the electrode to detect dopamine is shown here. So first figure on the top left shows the current versus voltage when it is exposed to a certain concentration of dopamine, the carbon nanofiber electrode. The middle figure shows the calibration plot, the current versus the concentration of the dopamine. So this carbon nanofiber electrode is capable of detecting dopamine, and also in a selective fashion compared to other neurotransmitters such as serotonin, because typically these neurotransmitters like dopamine and serotonin they are present in a sea of ascorbic acid. The next slide shows the ability of this carbon nanofiber electrode to discriminate among dopamine and serotonin and ascorbic acid. The conventional glassy carbon electrodes, which are the most common electrodes and they've been around for decades, those electrodes can individually identify dopamine and serotonin and ascorbic acid in laboratory studies, but when you have all three of them, present at exact concentrations as you have in the brain, these old are conventional glassy carbon electrodes. They are not able to distinguish the peaks arising from these individual components. On the other hand, the carbon nanofiber electrode, without going into the details, you can look through this. They can identify individual peaks arising from dopamine and serotonin and ascorbic acid in an unambiguous way. And so in that sense, the carbon nanofiber electrodes have tremendous potential in our development of deep brain stimulation procedures to provide a closed loop system where you can measure the concentrations of these, and then when you see deviation from normally expected values, then stimulate the portion of the brain in order to achieve the desired results. Some of the other applications for nanobio, and particularly for carbon nanotubes, one application in the ophthalmology area, it is called retinal cell transplantation. As we grow old, many of us begin to lose our sight. It is called macular degeneration. And in this case, what happens is that the retinal pigment epithelial cells, they begin to die. What it is it doesn't happen overnight. Nobody goes blind overnight. It is a slow process where the cells die, leading to the loss of photoreceptors in our eye. So the solution for that, the medical community came up with a solution. Why not replace the cells that we lose? Okay, and so what happens is, when macular degeneration is identified, then the surgeon can harvest these cells, good cells, from your own eye, and then grow it in culture in the lab, and then put it back now, to make up for the cells that which are dead. So this is called autologous transplantation, which is basically transplantation using your own cells. So sounds like a good idea, okay, but there are some problems. What it is harvesting your own cells from the eye is not a problem, but when you try to grow that or culture them in the lab to grow these cells, so you can put them back in the eye, these cells in a petri dish, they fail to establish a proper architecture. There is a certain architecture of these cells in our eye, and so when you fail to get that architecture, you just get a jumble of cells, and that is totally useless. So what is the solution for this? How do you establish a proper architecture? So then, instead of growing them on a petri dish, just grow them on a physical support. So what is that physical support going to be? Natural substrate is obviously the choice. It could be a basal laminar or posterior cornea. So these are natural substrates. So these substrates allow you to get excellent architecture when you grow the retinal epithelial cells. So you really get the architecture that you want. So there is another problem. When the surgeons try to work with these during surgery, these substrates, these protein-based substrates or the natural substrates, they tend to curl up. Okay, so they are very difficult to manipulate, and they also lack the mechanical properties necessary for surgical handling. So one solution for that is carbon nanotube-based paper. The nickname for this paper is Bucky paper. What I'm showing here is it is about 0.5 centimeter by 0.5 centimeter, but you can get the right size that you want. So it is a mesh of carbon nanotubes in a paper-like structure. So now you grow the epithelial cells on this substrate. Here you not only get the proper architecture that you want, so that's what you see here. The as-prepared Bucky paper is on the left image, and then after you stain that with the epithelial cells, that is the middle image. The last image on the right, that shows a light micrograph. And so you get a very confluent monolayer of the cells with uniform orientation and excellent attachment of the cells on the bucky paper, and you get the type of architecture that you can get on the natural substrate. So this image shows the implantation of the nanotube bucky paper in the subretinal space of an albino rabbit, and the surgeons found it easy to manipulate this substrate during surgery. It does not tend to curl up, it stays pretty flat, so it has all the desirable mechanical properties that you need for handling during surgery. And the bucky paper also was very well tolerated by the rabbit, so no inflammation, no problems over a long period. Okay, so this gives you an idea that this bucky paper is biologically compatible. So you can think of applications in terms of wound healing and many other biomedical applications where you need a biocompatible substrate. Finally, I would like to talk about the so-called U-health or ubiquitous health, or the Europeans tend to call it e-health. I talked about all kinds of biosensors or nano in biomedical applications. How do we make use of them in smart home? So people have been targeting two specific ubiquitous health services. One, the first UCare service is assisting elderly people at smart homes and help them to live their day-to-day lives in a safe way. Okay, so that is a smart home for elderly people. And then the second one is continuous monitoring and diagnostic services. Essentially, monitoring clinical conditions of patients in a proactive manner to detect any symptoms before the situation becomes catastrophic or serious. There are many things implantable in a body, and there are also body sensors. For example, it could be eye implant, cochlear implant, heart implant, blood pump, air pump, and foot implant, force actuators, and shoulder implants, and then also a variety of different sensors. The innovative approach that is being pursued in many universities, and the one that I'm showing here is from a Korean university, Pohang University of Science and Technology. So the innovative approach here involves in the smart home have a lot of physical sensors to monitor light and temperature and the environmental conditions, gas and vapor sensors to monitor the air quality, and also things like carbon monoxide for safety. In addition, it could be implants that I showed in the previous slide, and then lab on a chip for clinical diagnostics. So this continuous monitoring then can be communicated via internet or through smartphone to the healthcare providers. So that is an innovative approach. So this is an apartment actually built by the graduate students at Postec, with some of the detectors, the gas detectors that I talked about, and smoke detectors and RFID tags and appliance control, and then physical sensors that monitor heartbeat and motion, blood oxygen levels, and other things. Again, there is a long way to go in terms of getting feedback from some of the body implants or lab on a chips, but the smart home is beginning to shape up using advances in physical, chemical, and biological sensors. To summarize, nanotechnology is an enabling technology which will have an impact in all the economic sectors, but one of the most important sector with a great deal of potential is the health and medical sector. Some of the examples include nanomaterials for drug delivery, early warning sensors, lab-on-a-chip systems, implantable devices, and artificial parts with improved characteristics the nanomaterials such as carbon nanotubes, graphene, and silicon nanowires and zinc oxide nanowires. They all have tremendous potential, and they show promise for use in sensor development, use as electrodes in biomedical applications. So there is a tremendous effort going on across the world. Because of the expected impact, there is a large research community devoted to nano bio applications. So you can look forward to the improvements in situations in medical devices and healthcare diagnostics in the coming decade.